Alright, welcome to the fifth installment of the forces unit. So we're going to talk about tension. So we've learned about Newton's first law, second law, and third law. Now we're going to get into specific forces and how they all connect to those laws and how to solve the problems with these forces. So the first one is tension. Tension is an easy one to pick out because if there's a string or a rope or any sort of wire, then you know you're going to have a tension force. One assumption that we make with our wires, and this is just to make our lives more simple, is we assume them to be massless, so that way there's no force of gravity acting on them and impacting the system. So they are massless strings, they never stretch, they're perfect strings all the time, so they're simple. So let's look at this situation of just a block hanging from the string and the forces that are acting on it. So the forces, we would have force of gravity pulling it down, and as we said before, we'd have a force from the string pulling it up. That's because we have to know there's a force going up because Newton's first law, it's not moving, the forces are balanced, so there has to be a force up. It comes from the string. This force is what we call tension, this string up force. So now instead of calling it the force of the string, this would be the force of tension, and then we have the force of gravity going down. Now, what about the forces on the string in the middle? So if we think about it, there would be tension in both up and down. So there'd be tension from below and above. So another assumption that we make with ropes, and it comes from this idea, is the tension force at one end of the rope is the same at the other. So the tension here is the same as the tension here. So that's how the ceiling feels the full Fg from the block hanging below it. So let's take a look at an example with a tug of war. Lots of people think the harder you pull on the rope, the better you'll do in a tug of war. Well, this is not the case. It's actually something different that you need to do to win a tug of war. So in our situation here, we've got one person pulling on each end. We're going to assume the rope does not move. So the force, there's a force of tension this way on the rope, and there's a force of tension this way, and we are applying a force in the opposite direction. So that's our free body diagram. If we're not moving, those forces have to be balanced, and these have to be balanced as well. So these are equal. As long as the rope does not move, they are equal. So then the question is, how do you win a tug of war? If the force of tension is going to be equal on both sides no matter what, so no matter how hard you pull on the rope, it's always going to be equal on the other side. The way to win comes where the other place where you can apply a force, which is here on the ground. So if you push on the ground here and here, if you're pushing down on it, you feel the force pushing you back. And that's how you win a tug of war. If you push down on the ground pushes back on you in the equal and opposite way. So if you're pushing down, it's going to push you up. The more you can push sideways, the better you're going to do. So it all comes down to pushing on the ground. If you lose traction on the ground, you are just not going to win the tug of war. So keep that in mind next year when it comes time for the tug of war competition at the house picnic. Let's take a look at an example. So we've got a 50 kilogram bucket being lifted up by a rope. The rope will not break if the tension is 525 newtons or less. The bucket started from rest and is lifted 3 meters and moving at 3 meters per second. if the acceleration is constant, will the rope break or not? So we've got our list of givens. I've listed Ft here as less than or equal to 525 newtons. That helps me know that I don't actually know what the force of tension is. I want to compare it to 525. So I have to figure out what the force of tension is. And I also don't know my acceleration. We know it's constant, but we don't know it. So let's draw our free body diagram. Fg going down, always. That should be your starting point no matter what. If we're a bucket being lifted up by a rope, that rope is applying some tension. And that's our other force. It's not an applied force. Now we're calling it force of tension because it's coming from a rope. So that's our free body diagram, and that's all there is to it. So now we go to the same starting place as always. F net equals ma as vectors. Now ma, adding our forces Ft plus Fg, still as vectors. Now let's take away our vectors. What direction we want to make positive? Let's make up positive because we're moving up. So then we get Ft minus Fg equals ma. Now if I get Ft on its own, I would get ma plus Fg, which is equal to ma plus mg. Now, if I had the acceleration, I'd be able just to solve this and get my number, but I don't have the acceleration, so I have to solve for it right now. So let's find A. We've got to find our acceleration. We know velocity, we know the initial and final velocity, we know the distance. The equation we want to use is the squared one. V squared equals V naught squared plus 2AD. Got to rearrange it for the acceleration. Subtract V naught squared, divide by 2D. So we get acceleration is V squared minus V naught squared over 2D. So plug in our numbers, 3.0 meters per second squared minus 0 over 2 times 3.0 meters. 9 divided by 6, we get an acceleration of 1.5 meters per second squared. Now we know our acceleration. Now we can take that, put it into our equation. Our mass, 50.0 kilograms. Acceleration, 1.5 like we just calculated. And plus our mass again, times 9.8 meters per second squared. We calculate that up and it will give us 565 newtons. Now this question, we actually don't need to worry about sig figs. The sig figs would come out to 2, but we don't need to worry about them because that's not what we're asked. All we're asked is the rope in danger of breaking? And if the force of tension here is 565 newtons, it is greater than the force that says it will not break. So yes, it is in danger of breaking. Always start force problems with the same spot. F net equals ma. Figure out what your forces are. If you don't know the acceleration, use your kinematic equations to find the acceleration. Take a look at these 3 questions in the textbook. You'll also find those 3 as your homework on formative. So either place you want to do that, doesn't matter. Physics is awesome, and enjoy.